So this is, I think, session number 8, right, if I'm not mistaken. So let's start by understanding the absolute basics of the concept of relative motion. So relative motion basically involves okay, Mansi. I will give you some hints about that. Okay. Yeah, so relative motion is basically about the equations of motion as seen or as observed relative to a moving reference frame. Okay. So at this stage, you have done Newton's laws of motion and you have seen something called non-inertial reference frame over there. So you're already familiar with the idea that one reference frame could be moving with respect to another. Though, of course, in the case of non-inertial frame, it should not only be moving, but it should be moving with acceleration. So the definition of a non-inertial reference frame is that it is accelerated with respect to the inertial or ground frame. Here, the definition of a moving frame is just that it's in motion. It doesn't matter whether it's having zero acceleration or non-zero acceleration. If one reference frame is moving with respect to another, then we will say that when we write the equations of motion in the second one, we have to write relative equations of motion. Okay. Now, again, like you might have discussed in the case of inertial and non-inertial frames, you realize that there's no such thing as the absolute frame as far as the universe is concerned. Because in the universal situation, it's very difficult to define absolute rest, because if you're talking about the earth is in motion with respect to the sun is in motion within the solar system. So that is like an infinite loop. Okay. But since most of our physics is in reference to our human experience, which is on the surface of the earth, we can treat the surface of the earth, or what we call the ground frame, as an absolute frame. So any reference frame, especially if you're talking about an experiment happening on earth, if the experiment is happening in space, then it's a slightly different situation. But if we are doing any experiment on earth, so any reference frame that is moving with respect to the ground, okay, with respect to, in earth's frame, the ground is a fixed reference frame, so that becomes the absolute frame. So any frame that is in motion with respect to the earth's surface, or the so-called ground frame, becomes what we call a moving reference frame. So equations of motion written with respect to or relative to a moving frame, those equations comprise what we call relative motion. So let's understand it in this sense that, suppose what I've drawn here is my absolute reference frame. So this XYZ system is the ground frame. So this is the ground frame. Now within this frame, I have referenced 2 points or 2 particles, let's say A and B. So one of the particles is located at the position B. And one of the particles is located at this position RA. So in the most general situation, we'll assume that both A and B are in motion. So this one is moving with some velocity of its own, some acceleration of its own. This one is moving with some velocity. Oh, sorry. This one should be A and BB. Right. So they are having some individual velocities, accelerations, etc. Okay. Then we start by defining the position, or what we call the relative position actually. Relative position, let's start by defining for B, that is the relative position of B with respect to A. How would we define that? Okay. So now you understood what position is in the original sense. With respect to the ground frame or the origin, the position of a particle is just the vector joining the origin with that particle. So now the thing is that when we're talking about position of B with respect to A, it's like we are shifting our origin from O to A, okay, because our reference frame is now fixed to A. So it's like we're talking about what is the position of B, but not seen from the origin, but seen from A. So in that sense, it becomes something very simple. It is nothing but this vector, the vector which is B from the position of the particle E. So this becomes what we call the position of B with respect to A. Now the notation is important over here. When we talk about relative position of B with respect to A, we will write it as R vector B comma A. So this notifies the fact that it is of B, but with respect to or relative to. Okay, so whatever relative quantity we are referring to, we'll write in this notation. That's one with respect to another. So if it's 1, 2, it is position of whatever that 1 is relative to whatever that 2 is. Likewise, if you're writing A12, this is relative acceleration of 1 with respect to or relative to 2. So that is the notation we'll use. Okay. Now that's the notation. Now coming back to the diagram, you can see that this vector is nothing but the difference of these two vectors. So that becomes the definition. The mathematical definition becomes this. So the relative position of B with respect to A is like this, where RB and RA are position of these two with respect to the common ground floor. Position of B with respect to ground floor. This is position of A with respect to ground floor. So if I know the absolute position vector of B and A, then I can write the relative position of B with respect to A as a difference over. So very simple. Suppose we have a situation where B is located at the point 5, 4 in meters. A is located at the position 1, 2 in meters. Okay. We have to find the position of B with respect to A and also the position of A with respect to B. And you can see here that RBA defined like this will just become 5 I cap plus 4 J cap minus of I cap plus 2 J cap. So very simple, it becomes this quantity 4 I cap plus J cap. So this is, so if you are located at A, with respect to you, the position of B would look like this. It would be 4 units along the x-axis plus 2 units along the y-axis. That would be the position of B with respect to A. Okay. So just make a quick note of this or note of the key points here. And
So
also find out this second. Yes.
So when the vectors are moving towards each other, don't we take relative position as RB plus RA?
No, beta, that is relative velocity, and that will become, actually the definition is still VB minus VA. But what we'll see is that if they're moving towards each other, when we do the addition of the components will actually add.
Oh, okay.
You're
So we're
understanding the
not
point?
taking the sign in that one.
Yeah. So the vector is always written with the minus sign. But
Yes.
suppose they're opposite, then actually the quantities get added.
Yes. Okay.
Understood?
Yes.
Okay. Okay. So just find out the second quantity also, RA with respect to B. Right, that's correct. Okay. So one thing you'll observe is that always RAB is minus of RBA because the definition is only that way. Okay, so yes, as I'm sure all of you would have worked this out, RAB, which is now going to be RA minus RB. So in that same diagram or in a similar diagram, if A is, for example, located at 5,4, so A is probably somewhere here, and B is located somewhere here, 1,2, so it's probably somewhere here. So the position of A with respect to B oh sorry, it's the other way around. This is and this one is B. Yeah. So the position to B is this vector that you can see through the formula will become minus 4 I cap minus 2j cap. So in general, you can see that always position of A with respect to B is equal and opposite to position of B with respect to A. They are equal and opposite vectors. If one is like this, then the other is like this. So this is just position. So it's like a way to reference. Now the actual part of motion starts. Okay. So we go in the same sequence that we've seen in kinematics. Once you have defined position, the next thing we'll define is displacement, but this time we'll define relative displacement. So this will just be defined as the change in relative position. Okay. So basically we can say that displacement of B with respect to A is delta of position of B with respect to A, or we can say that in a certain time interval, this is RBA final minus RBA initial. Okay. But the better way to understand this is that when we write displacement of B with respect to A as change in position, from here we can see it is change in position of B minus position of A. Yes, and we will scroll up. this one. So this displacement will become delta of RB minus delta of RA. That you can see will become the displacement of B in the ground frame or in the absolute frame minus the displacement of A. So it's a very symmetrical definition. You have seen that position of B with respect to A is difference in the absolute positions. So like that, displacement of B with respect to A. Just apply the change to the above equation. So delta of left hand side is equal to delta of right hand side. So this should just become delta of RB, which is SB, minus delta of RA, which is nothing but displacement of A. It's very simple, logical way of understanding this. Now we'll see this with examples also, and this is where what we were talking about a little while ago, what you were also asking, that if they're in opposite directions, it adds up. So that will come up in the vector definition. Okay, if SB and SA are vectors in the opposite direction, so when we do this calculation, the actual magnitudes will add up. Okay, so that's how it works. I'm just scrolling up for a bit. Come back to this.
Done, sir.
Yeah. Okay, so let's understand this with a couple of examples. Now, suppose we take very simple possible situation that on a horizontal plane along a straight line, two people are moving. So let's say A is located here and B is located here. This is the situation at t equal to 0. Now, after some time, let's say A is located now here at time t equal to whatever 2 seconds, and A has moved by a displacement of 5 meters. But during that same time, you can see that B has moved by a displacement of, let us say, 12 meters. Okay. And in one dimensional notation, I'm showing both with only as scalar quantities. Okay. Now I want to find that what is the displacement of B with respect to A, or actually it's one dimensional, so I'm just writing in scalar notation. Okay. So this quantity. So let's understand this conceptually first. So what is happening is that as far as A is concerned, in A's frame at t equal to 0, B was located somewhere here. So this was position of B with respect to A. So let's say it was some X. Now you can see that at the new time in A's frame with respect to A, what has happened? The position of B with respect to A has changed. Okay. This new position, okay, at t equal to 2 seconds, you can see that in the above diagram, you can see it is the original position, whatever this was X. This was X. So this is becoming x plus 12 minus 5, becoming x plus 7. So this is becoming x plus 7. So what A is saying that B is displaced by is this. This is the displacement of B with respect to A.
So what will we mean by this when we talk about two-dimensional movement?
I'll come to that. Okay, so this, once we understand this in detail for 1D, now it will make sense in 2D, 3D also. Okay, so that's the whole idea. Okay, so this is the logical way of understanding this. That imagine you are the person A who's walking like this, and you walk 5 meters in 2 seconds, but the person B is somewhere in front of you, and you don't even know exactly how much in front, because the question is not giving you the value of x. But you see that that person has walked 12 meters in the same direction as you along the same line. But that 12 meters in the ground frame, while you have walked 5 meters. So you will not observe them moving 12 meters actually. You will feel that they moved away from you by only 7 meters. So this example is clear, no?
Yes, sir.
Okay. But now let's also understand it by formula method. Okay. So by formula method, what is happening is we can see that from 0 to 2 seconds, what are the individual displacements? The individual displacement of A is plus 5 meters and the individual displacement of B is plus 12 meters. So the relative displacement of B with respect to A should be the difference. So it should become 12 minus 5 or plus 7 meters. Okay, which agrees with what is the logical picture you're seeing also. Okay, so just make a quick, if you want to note down or otherwise just a run through of this concept and make sure this one is clear. Okay, this example in the application of the above formula, it's reduced to a 1D example. Okay, then we'll come to the 2 and 3D examples and we'll see how it makes sense there also.
Then sir, the relative displacement is actually just the vector subtraction of their final positions.
There, see, it is the vector subtraction of the displacement. Okay.
So why
It's
not
not a
final
vector
position?
subtraction. Final.
So for
So
B, it's x plus 12, and for A, it's x plus 5. Then if we subtract, we get second.
yes, this is final. Okay, minus initial. This is what you're saying. No?
Yes, sir.
Yeah, correct. No? So that is the definition. No? Displacement is change in position. No?
No, sir, not even relative to each other, sir. Even if we take it relative to the origin.
So then it is the relative to the origin, it is the displacement of B minus the displacement of A. No? And displacement is only C. So when you apply this quantity, it is delta of RB minus delta of RA.
Yes, sir.
Right? And that is nothing but SB minus S. So that is the sequence of the derivation.
Then, sir, can I say that relative displacement of S with respect to A, where P is any random point, I can take it as R BP minus R AP.
No, it is displacement's difference, but not position's difference. The difference in position is actually this thing. It is the relative position. You're understanding one point, better?
No, not so. Not the statement.
This is this. Okay, RB minus RA is relative position, whereas this. Okay. So how we get this lower equation? We get it by just applying the change to the above formula. Delta of the left hand side is equal to delta of the right hand side. So that's how we get it.
Yes, sir.
So in this example, in this part, I've shown it to you logically. In this part, I've shown it to you logically. If you draw a visual diagram, how this is looking. Whereas here, I've just applied the formula method. The above vector formula, I've reduced it to one-dimensional vector with just algebraic sign.
But sir, relative displacement actually is after some time has passed, how far away is B from A, right?
No, it is how much B has moved from A beta. Displacement is always that thing, na? Initial to final position. It is not the position. You're understanding the point, beta?
No,
See,
sir.
in the in the ground frame, suppose an object was here right now, okay, and after
Yes,
some time it has gone to the point A prime. So what is
yes,
the displacement? It is not OA prime, na? OA prime is the final position.
yes,
You
sir.
understanding? The displacement is this vector, na? A to A prime. So like that, okay. What is the relative displacement? So suppose you are the person A. So with respect to you, how much B has moved away? That is the relative displacement. Not where is B. How much B has moved away from
Okay.
you? That is the relative displacement. You understanding? So that's why come to the lower diagram. So at t equal to 0, where are you seeing B? You're seeing B ahead of you at some distance x. At t equal to 2 seconds, where has B gone now? It has gone to some that same distance x plus 7. No?
Yes, sir.
So what is the displacement of B in your frame? It is that extra position, you know, how much the position has changed by. So it has changed from x to x plus 7. So your conclusion that is that, okay, with respect to you, B has moved away by 7 meters. So the displacement is plus 7 in the 1D system.
I got it, sir.
Understood? So when you're doing this example, the one I've just shown, don't just now think about what happens in 2D. We'll understand with another example. Just focus on this example, okay, and just try to think of it logically. So you'll realize how both by the formula method as well as the logical method, you can see that as far as A is concerned, with respect to A, the displacement of B is 7 in the positive direction.
Yes, sir.
Now, similarly, you'll also understand that as far as B is concerned, the displacement of A would be how much? It would be minus 7.
Yes, sir.
It would be 7 in the negative direction because B would be initially seeing the position of A at minus x. And now he's seeing A at a position of minus of x plus 7. So it's on the negative side as far as he is concerned, and the position has increased by 7. So the displacement is minus 7. So this should be written in scalar notations. Okay, so hope this example is clear.
Yes, sir.
Okay, now let's move on to another example. Where now this is happening at t equal to 0. This is my origin. Now E is at that moment located at 5 meters and B is at that moment located at 15 meters. But A is moving with a constant velocity of 2 meters per second uniformly. And B is moving in this direction, the opposite direction, with a velocity of 1 meter per second uniformly. Okay. So now what we have to do is find their positions XA and XB relative to absolute or ground frame O. At t equal to 2 seconds. And from that, find displacement of A with respect to B and displacement of B with respect to A in the interval 0 to seconds. Okay. So you can do this question by just the formula kind of method also, or you can also do it by just visually drawing a picture because it's quite simple. There are two objects moving in 1D motion along the x-axis and that too uniformly without any acceleration. So Yes, Aparna, correct. That's good. Okay, so the answer to the first part is that at t equal to 2 seconds, the position of A would have changed to 5 plus 4. So that is plus 9. And the position of B would have changed to 15 minus 2. So plus 30. Okay. So at t equal to 2 seconds, you can see that A would have had a displacement of 4 meters, but B would have had a displacement of minus 2 meters. So from this only you can understand that S of A with respect to B or S of B with respect to A. So there is another way to understand. Okay. Or you can see that at t equal to 2 seconds, the position of A is equal to 9 meters. The position of B is equal to 13 meters. So the position of A with respect to B is how much? It is minus 4 meters. Okay. Whereas at t equal to 0, position of A was 5 meters, position of B was 15 meters. So the position of A with respect to B was minus 10 meters. Okay. So from this you can see that the displacement of A with respect to B from 0 to 2 seconds is the change in position of A with respect to B in 0 to 2 seconds. So that is position of A with respect to B at 2 seconds minus position of A with respect to B at t equal to 0. This is the displacement of A with respect to B. By this kind of method. So here you can see that if you were B, then what you would have seen is that initially at t equal to 0 with respect to you, A was over here. But by the time you came to 2 seconds, this. So this is your displacement of A with respect to B. You can see it's plus 6 meters. It's plus 6 meters.
Sir, noted.
Okay, so this example I hope is clear to all of you. Okay, how
Yes.
one is +6 and the other is, but again you can see because this time they are moving in opposite directions now. So the magnitudes actually add. So actually in ground frame A is only moving by 4 meters and B is moving by 2 meters. But relative to each other, they look like they made a displacement of magnitude 6 meters. Okay. So this actually lays the foundation to understand everything in 2D now. So for example, next is our first case of 2D. Okay. So let's say that we have this situation that okay, in the XY plane, or let's say that at t equal to 0, A was located here. Okay. At the position 2, 0. Okay. And let's take a very simple case where B was also located here. So A and B are both at 2, 0 at time t equal to 0. Okay. Abhinav, let me clear your doubt. Okay, beta. So what is happening for, I'll just go back to the previous example for a moment. Okay. Yeah, so we're talking about the second part, right? Displacement of B with respect to A.
Yes, sir.
So when you're applying this formula, you'll see that what is the displacement of B in ground frame? It is -2.
Yes.
And what is the displacement of A with respect to ground? It is +4.
Yes.
So that's how the relative displacement is becoming -6. Okay.
Okay, sir.
Now logically, what you're seeing now that here initially at t equal to 0, what was the position of A as far as B was concerned? Sorry, B as far as A was concerned. X of B with respect to A. In the above diagram, you can see it was this position with respect to this. So it was 15 minus 5. It was +10.
Yes.
Okay. And at t equal to 2 seconds, what the position of B with respect to A has become? It has become B has moved ahead by, moved towards by 15, and A has also moved towards by 4. So it has become, now the difference between this and this, it has become how much? It has become 10 minus 4 minus 2. So it has become +4. What is it now?
Yes.
So now you understood relative displacement kaise aa gaya?
Yes. Sir.
S of B with respect to A is X of B with respect to A at t equal to 2 minus the initial position. So you can see that that is becoming this minus this. So it's -6. So to A, it looks like B is come closer to him along the negative x-axis by 6 meters. Okay, I got it?
Yes, sir.
Okay. Now coming to this question, this next one. Now what is happening is that this is the position at t equal to 0 for my system. Now after some time, now let's say what happens is A sets off along the y-axis. So at some time A reaches somewhere here. And B during that same time sets off along the x-axis. So B reaches somewhere here. So at t equal to 10 seconds, let us say A is at the position, let's say 2, 30. And at t equal to 10 seconds, B is at the new position, which is let's say 42, 0. Okay. So given this information now, what we have to do is, first of all, find the displacement as a vector for A and B from t equal to 0 to 10 seconds. And secondly, find the relative displacement. S of E with respect to B. And find its magnitude. Yes, Anirudh, that's correct. Now, just your I cap and J cap are interchanged. Okay. Now work out the second part. I cap and J cap should be interchanged in your answer, Anirudh.
Yes, sir.
Yes,
Is the
Aditya,
answer correct?
yeah, Aditya, your answer is correct. Anirudh, your answer for the second part, that square root 1 you have sent, is not correct, beta. Okay. First, write it as a vector quantity, na? Displacement of A with respect to B. Then calculate its mod. Yes, Anirudh, your answer is correct. Aryan, your answer is correct. Very good. Vedant, your answer is correct. Janvi, correct. Very good. Okay. So see, for the first part, you can just see that A moves from 2,0 to 2,30. Okay. So therefore, the displacement of A during that time is 30 j cap. Okay. And B similarly moves from 2,0 to 42,0. So displacement of B is 40 I cap. Okay. So once you got this, you can just understand this is in 0 to 10 seconds. Okay. So now you can understand just formula wise the displacement of A with respect to B is displacement of A minus displacement of B. So it is minus 40 I cap plus 30 j cap. From 0 to 10 seconds. And therefore its magnitude simply 50 meters. Now I'll explain this logically also. So basically what this means that the interpretation of this is that to B, it looks like he has displaced by this is what this means actually. The interpretation of this is like this. Okay, so here let's compare the two pictures. So initially at t equal to 0, say both A and B are at the same position. But at a later time, B is located here and E is located here. So what is happening that at t equal to 0, okay, position of A with respect to B is 0 now. A is where B is located.
Yes, sir.
But at t equal to 10 seconds, you can see the position of A with respect to B has become this vector. Which is minus 40 I cap plus 30 j cap. So as far as B is concerned, if your reference frame is stuck to B, then what you'll see is that A was located here initially. Oh, sorry, A was located right against you at t equal to 0. And now A has moved to this position at t equal to 10 seconds. Let's move to this position. So this only is the displacement. Okay. So displacement of A with respect to B is the final position minus the initial position. Okay, so now I hope the vector relation also makes sense in 2D. How come we are able to interpret the relative displacement as the individual displacements in ground frame subtracted? Yes, Janvi, you have a question, beta?
Yes, sir. Sir, can we consider this also as A feeling like it's not moved at all? And so
B.
the new A dash, we can make them coincide, and so B will move down.
Yes, yes, yes. So if you look at the displacement of B with respect to A, what will that have been? That will be individual displacement of B in ground frame minus displacement of A. So that will be like this. It will be 40 I cap minus 30 J cap. So if your reference frame is fixed to A now, then what you will see is B was here initially, and now with respect to you, B has moved to this position.
Yes, sir.
So this is where B is at 10 seconds. That's just equal and opposite to this vector. S of B with respect to A, on the other hand, will become 40 I cap minus 30 J cap. Yes, Dhruv, I'll scroll up after this. Okay. Okay, so what I want is, like, it should be clear to you both from the formula method, how we have actually calculated SAB or SBA by using this formula here, this one. This is the formula. So we use this formula, but also in terms of interpretation. Okay, this is the interpretation of it, that if you're this one here, here we are able to visualize it because it's quite a simple situation, even though it's two-dimensional, so it's not as simple as 1D, but still we are able to visualize it, that A was, as far as B is concerned, A was located right alongside it, but at a later time it's moved to a position where B has to look in that direction to find A. He has to look and he'll see that A is 40 meters behind him along the x-axis, but 30 meters above on the y-axis. So the relative position has changed from 0 vector to this vector, which is minus 40 I cap plus 30 j cap. So that is the relative displacement. Okay, so Dhruv, you want to see this part, right? The solution part or the question?
No, sir, solution part. Yes, sir, done.
Yeah. Okay, done?
Yes, yes, sir, it's done now.
Okay. Okay, now let's see this in an interesting application example. So what we have is this kind of situation. Now a person A who is at rest throws a ball like this at t equal to 0. And another person B is running at a uniform velocity like this on the horizontal ground. Okay. So A is stationary and at t equal to 0 projects a ball at u equal to, let us say, 20 meters per second, theta equal to 37 degrees. B is running at constant velocity of magnitude let us say the magnitude is 4 meters per second. Okay. Now assume the projectile and B move in the same vertical plane. Remember, we've discussed at length that projectile motion is actually a two-dimensional motion. It happens in a certain vertical plane. Okay. Take the value of G as 10 meters per second square. Find the displacement of the ball relative to B from 0 to 2 seconds. In this time interval of 0 to 2 seconds, what does the displacement of the ball look like to B, not to A, but to B? You can use the standard XY axis like we take for projectile motion. So you can take the horizontal axis as your X axis and the vertical axis as your Y axis, so that your U vector and G vector, they're lying in that XY plane. So in this case, the velocity of B will also lie in the same XY plane because the motions are coplanar. They're happening in the same plane.
So is my answer correct or wrong? Sir?
Okay, so I'm just verifying the answers, people. Okay. So what you will see that from 0 to 2 seconds, okay, the projectile would have made a displacement like this. Let's say it's here at 2 seconds. So the displacement of the projectile or the ball would be like this. Okay. And B would have displaced to somewhere like this. So the displacement of B would be like this. Okay. So it doesn't even matter where we are taking our origin. As long as we are taking our XY axis like this, we can see that from 0 to 2 seconds, the displacement of the ball in the ground frame would be U cos theta T. Okay, so that is 20 cos 37 into 2 I cap. Okay, plus U sin theta T minus half GT square. So that would become 16 into 2 I cap plus 12 into 2 minus 5 into 4 J cap. So 32 I cap plus 4 J cap in meters. This would be the displacement of the ball in the ground frame. Okay. Just verify my calculation once. Okay. Now in the same time interval, the displacement of the person B would just be minus of PB into TI cap. So the displacement. Right. So the displacement vector B, now how much is B's velocity that we have taken? 4. So minus 8 I cap. So the displacement of the ball as seen by B would be displacement of the ball minus the displacement of B in ground frame. Yes, correct, Harim.
Sir, isn't this somewhat like the pseudo force concept that we learned?
Actually, pseudo force is a repercussion of this relative acceleration thing. I'll explain to you later. Okay. So what happens is now when we convert this displacement concept to acceleration concept later. So what happens is that the acceleration of an object B with respect to A is the acceleration of B minus the acceleration of A. Okay. So when you convert this to Newton's laws, the mass into acceleration of B with respect to A, this is in the non-inertial frame, becomes the acceleration of B in the ground frame minus the acceleration of A, which is basically the acceleration of the non-inertial frame, but M into this. So that's why we write this. So this is the net external force, but this becomes the pseudo force. So that becomes equal to mass and relative acceleration. Okay. So we'll understand when we come to relative acceleration. I'll explain this in more detail. Okay, but this is how, this is the logic of adding that. Apart from the fact that intuitively you can understand that when you are in a non-inertial frame, your body experiences pseudo force. Just like, you know, when you're sitting in a bus and it's at rest, but suddenly it accelerates, your body feels pushed backwards.
Yes, sir.
Or you're moving in a bus, moving at uniform velocity, when it suddenly breaks, you feel that push forward. So that is the like physical experience of pseudo force. But what is the logical explanation of it from the laws of physics point of view? So it actually comes by application of relative motion concept.
Okay, sir.
In Resnick-Halliday, if you study that part about the application of pseudo force and the whole concept of non-inertial frame, they've explained it in this manner only, using relative motion concept.
Sir, I use that only to solve this question. Pseudo force, everything.
Okay. You can do that. Nice. You can rederive the equation of the projectile using pseudo force. But see, here there is no pseudo force because you're assuming B is moving at uniform velocity.
No, sir, not pseudo force. Sir, I just took it as pseudo displacement. So
Okay.
for the man, the
So
ball is
basically,
moving.
so that's relative displacement only. No, what you are calling pseudo in our language, it's nothing but relative displacement only. But yeah, this concept is similar. Okay, so hope the application of relative displacement is now clear to everyone. Okay, using this.
Sir, I wanted to ask the height of body A from the horizontal doesn't really matter while calculating the relative displacement.
Yeah, displacement के लिए it doesn't matter, na, beta, because displacement is change in position. Now, if I asked you what is the relative position of the ball with respect to B, then of course the height would be taken into account, right?
Yes, sir.
Sir, so the final answer must be 40 meters.
No, the final relative displacement in vector form is this only, na, beta, 40 I cap plus 4 J cap. Now, if I wanted to calculate the magnitude of that, then it would be square root of 1616, 1616 square root.
Yes, sir.
Now, just as a reminder of one important concept we discussed, if I want to calculate this magnitude and I want to calculate it to sort of an approximate value instead of as a 4 square as a square root kind of term, then I can use binomial approximation method. Okay. What I can do is I can take 40 common here. So this will become square root of 10 plus, square root of 1 plus 1 by 10 whole square. Okay. So that is 40 into 1 plus 0.1 to the 0.1 squared. So that is 0.01 to the power half. So here I can use binomial approximation. So it is approximately 40 into 1 plus 0.005. So 40 into 0.005 is how much? 20 into 0.01. So 0.2. So it is approximately 40.2. Now, if you use a scientific calculator to do an approximate calculation of mod of square root 1616, you will see that you'll get this answer.
So can we just vectorially subtract the velocity of the boy from the ball and then multiply it by 2 seconds?
No, beta, because it's accelerated motion. No? So we cannot say displacement is velocity into time. You're understanding the point? If it was not accelerated motion, suppose these were two motions happening in a horizontal plane at constant velocity, then I could have said that okay, relative displacement is relative velocity into time.
Yes, sir.
So that's why if you use that relative velocity concept over here, it will go wrong. If you have to write it in that sense, then you have to also take relative acceleration into account.
Yes, sir.
Okay. And the acceleration of B is 0, no? Whereas acceleration of A is G. I mean, the acceleration of the ball is G. Okay, so that's how it works. Okay, now very good. So now that we've understood relative displacement concept, now we are ready to move on and understand the next two things, which is relative velocity and acceleration. Both the things we'll understand together. So let's start with relative velocity. So as far as the kinematics definition is concerned, it's very simple. Velocity was defined as rate of change of position, which is the same thing as rate of change of displacement, instantaneous rate of change with respect to time. So relative velocity of, let's say, B with respect to A is just instantaneous rate of change of position of B with respect to A, or you can write this as displacement of B with respect to A also. Okay. So further, we can express this as position of B in absolute frame minus position of A. Take the differentiation operator inside, and as you might have guessed, it becomes the difference of the velocities. So again, relative velocity is, sorry, this last one is RA, not VA. Okay. But yeah, when we differentiate it, it will become VA. So ultimately, it becomes absolute velocity of B in ground frame minus absolute velocity of A in ground frame. But again, remember, it's the vector difference. Okay. So for example, if they're moving in a straight line towards each other, they will actually add up in magnitudes. Okay. So similarly, if you take this, and likewise, we'll do relative acceleration also. So this is the rate of change of relative velocity. So it becomes the instantaneous rate of change of the difference in their velocities. So once again, the same kind of steps. So now we can approach the previous question by using this type of kinematics also. We will find the velocity of the ball with respect to the moving object B or the moving person B as a function of time and integrate that to find the displacement. Okay. Or we can go on to find the relative acceleration and rederive the equations of motion. That way also we can do. So actually the definitions you will see just logically follow from this. Position of B with respect to A is position of B minus position of A. So now in this equation, if we apply delta on both the sides, we have displacement of B with respect to A. And if we apply instantaneous rate of change on both sides, so we have and similarly, if we double differentiate this with respect to time, so calculus wise, it's very simple definition actually. The moment you have understood what relative position is, from that it follows what is relative displacement, what is relative velocity and acceleration. Okay, so with this, like we are done with the definitions and concept set of relative motion. Of course, we'll discuss a lot of applications and problem solving tricks as we move along now. But we are coming towards the close of kinematics in general. So anyhow, let's understand a couple of very interesting examples of application of relative motion. So this is like the top view of a road, okay, like a straight highway, like an expressway. Now, let's say we have a longish kind of vehicle like a trailer truck or something, which is moving at a constant horizontal velocity of 36 kilometers per hour uniformly at t equal to 0, it is here. And we also know that the length of this truck, let's say 25 meters. Now at that very moment, there is another vehicle alongside which is just beginning to overtake this. So it's just about alongside, like this. So this is a car. Now this car is moving also at a uniform velocity of 72 kilometers per hour, just double. And the car itself is 5 meters long. This is the situation at t equal to 0. So we have to first of all find the velocity of the truck as seen by the car and the velocity of the car as seen by the truck. We have to find the time after which the car has completed overtaking the truck. Okay, and the road length, that is the length of the road utilized to complete the overtake. So I'll explain the last part in detail, but try to understand it from the language of the question itself. Okay, and try to figure out this question. It's very interesting. So especially for the second part, you might want to use the whole concept of relative motion. You can of course solve it from ground frame point of view also, that how much time it takes to complete the overtake. But it will be more interesting as well as quicker to solve it from the relative motion point of view.
So in the page above this, I forgot to write the thing you wrote in the column on the side.
Yes, very good, Dhruv. Janvi, your answers are correct. Okay. So basically, you can see that with respect to ground, the velocity of the truck, when you convert that to meters per second, it is 10 meters per second, and the velocity of the car is 20 meters per second. So the velocity of the truck as seen from the car's frame is minus 10, and the velocity of the car as seen from the truck's frame is plus 10. So basically, if you're sitting in the car, you will see the truck moving like this for you. And on the other hand, if you're sitting inside the truck, then you will see the car moving like this. So that is why for the second part, you can understand it this way, that suppose I'm observing from the truck. So in the frame of the truck, this is where the car is at t equal to 0. And it's moving at 10 meters per second. Now, from this point of view, when the overtake is complete, the car has reached here. Just about completed. So the car has moved relative to the truck by this much. This is the displacement of the car with respect to the truck. So you can see that that is equal to the length of the truck is 25 meters plus the length of the car is 5 meters. So motion of the car relative to the truck this is a uniform velocity. So displacement of the car with respect to the truck, that uniform velocity into time. So this should become, because at t equal to capital T, when the overtake is just completed, the displacement of the car as seen by the truck should be equal to its own length plus the car's length. So T should be equal to the time is 3 seconds. So this is the relative motion method of solving this question. You can also solve it from ground frame point of view, which will also explain the third part in more detail to you. So if you're in ground frame, this is where you see them at t equal to 0. And after some time, see them like this. So this is the displacement of the car, which is 20t. And This is the displacement of truck, which is 10t. So again, and this is the length of the road. Is utilized. So the road length you can see is the displacement of the car plus the length of the car. "65 meters of road length is utilized, because the entire portion, the patch of the road that you are using is from this section right up to this section. This is the section of the road that you are utilizing to complete the overtake. So here also you can see that you can derive this result this way also. But for the time, at least for the time to complete the overtake, it's much easier to put your reference frame in one of the moving vehicles so that that one becomes stationary for you and you're observing the second one relative to it. So hope this question is clear, people. Just make a note of it, and with this we conclude today's session.
Sir, is this counted as a difficult question?
Once you do a lot of questions in relative motion, you'll see this is not difficult. Right now it might be a little tricky, but in general
This is
it will
not difficult. That's what.
Yeah, it's simple in that sense. It's quite simple.
Okay, sir. Okay.
So,
Will you be sharing difficult questions?
Ibrahim, was that you? You had a question?
so I wanted to know, like in major test, what exactly, like till what part will kinematics?
Up to projectile motion, including projectile motion on inclined plane. So basically everything that we have discussed up to the previous lecture. Today's
Okay,
lecture's content is not there. Okay. So what you do is this week I'll also be sending some revision exercise today for projectile motion and 1D motion combined. So that entire thing, you concentrate on those revision exercises, and if anything is pending from HC Verma or the projectile motion worksheet which I've sent previously, do all that, complete all that, and make sure your doubts are cleared on the doubt lecture that we have this week, extra one. Okay. And I will also send you some material that you can, like some questions and all of relative motion, but you can pick that up after this thing is over, after the major test is over. This week I would like you to concentrate on the major test portion, especially because you are going to also have an JEE Advanced paper along with the JEE Mains paper. So JEE Advanced paper, the question patterns will be like you have in your exercises of module, which is multiple choice with more than one option correct. Then there'll also be comprehension passage questions. There will also be matrix match questions or column match questions. So just also concentrate on getting used to those patterns of questions. Okay.
Then, sir, will you be sharing the JEE advanced level questions for projectile, or we've already done them?
Yeah, I mean, now you can pick up from module. So I will give JEE Advanced pattern questions you can pick up from the module. And at a later stage, when you complete the module, we will also be doing some questions from DC Pandey.
So what from the module, sir? Window.
The exercise 2, 3, etc. They have the JEE Advanced pattern questions.
Okay, sir.
Right? So,
Thank you, sir.
okay. Yes, Dhruv, you have a question, beta?
Yes, sir. Sir, like I had a doubt in this question, sir. Like, why are we adding that 5 meters of car's length to that final answer of 60 meters? Because like that's our initial point. No? So why just 20 into 3 only?
We are asking what is the road length that is used. Now, see in the diagram that I made, the two vertical red lines that I have shown. That is the entire patch of the road that is used. Like from the bumper of the car where the overtake started to the front end of the bonnet where the overtake is completed. That is the entire patch of road that is used during the overtake.
Yes, sir. It's okay, sir. I got it. Okay.
Now, logically, you can see from the diagram that is equal to the displacement of the car plus its own length. Okay. So that you can see if you compare these two distances which I have shown. One is the displacement of the car 20t, this vector, and the other is the total road length. So the comparison will show you that this one is this plus 5 meters. So that's how the answer is becoming 65. Hope this is clear now.
Yes, sir. Yes, sir. And sir, one more thing that you didn't give us last time's class notes or recording. So
I will send the recording and the notes together with today's. Okay, I will send it today.
okay, sir. Okay, sir. Thank you, sir.
Okay. So that's it for today's session. People, wish you all the best.
Thank you, sir.
Okay.
Thank you, sir. Bye, sir.